Let us continue our discussion about big O notation, big theta notation, and big omega notation. Let's start with big O notation. Formal definition. Function at n is a big O notation g at n if and only if there exists a positive constant c and no or n0 such that 0 less than or equal to function at n is less than or equal to c times g at n for all n greater than n0. So basically, we could determine the growth of a certain function through big O notation through function g at n. This is the growth function of each function. So this is the function at n. So we have a formula that represents an algorithm, and this is the behavior of that algorithm. While CG at n, which is the big O notation, wherein we all know that this is the upper bound, the correspond to the worst case scenario, so it should be bigger. So when we plot it, it should be higher than the function f. So as you can see here, c times g at n at a certain point, okay, they are equal. This is your possible n sub 0 or n0. And beyond n0, g at n, cg at n is greater than the function at n. So any notation which is bigger than the function is considered as big O notation. Okay, so again, c times g at n is greater than the function at n, wherein n is greater than or equal to n0. Okay, so let's have an example. So we have a function of n equal to n squared. This is the growth rate of a function. And can we consider it a part of big O notation 2 raised to n? So again, 2 raised to n should be bigger so that it could be considered can be considered as the big O notation of n squared. So let's check for the value of n. So let's increase gradually the n. So n is equal to 1. 1 is the result for n squared. For 2 raised to n is 2. While n is equal to 2, so it will be 4 for n squared. 2 raised to n, 4. They are equal. So can we consider this as your n0? Let's check for the next value. So n3, n is equal to 3. N squared is 9. 2 raised to n is 8. So therefore, based on this transition, n squared is bigger compared to raised to n. So therefore, n is equal to 2. It's not your n0. So again, n0 is the minimum value or the start value wherein the g at n will become bigger compared with the function at n. Okay, then n4, now they are equal. So let's check again for the next value. N is equal to 5. 2 raised to n is now bigger. So can we consider that n squared is big O notation 2 raised to n? Let's check again for the next value. And again, 2 raised to n is bigger, and n raised to 7 is still bigger. So therefore, beyond 4, okay, if the value n is less than or equal to 4, it's equal. Beyond 4, and 2 raised to n is greater than. So therefore, f function at n squared is big O notation g at 2 raised to n, wherein n0 is equal to 4 based on this. Okay, for it starts beyond 4, it will be 2 raised to n is greater than. And the multiplier for g at n is basically 1. Okay, another example, 3n plus 2. And our g at n is equal to n. So we're going to determine if the given is a big notation of n. Okay, same procedure. So n is equal to 1, the result here is 5. Here is 1. So as you can see, there is no possibility that that n will become bigger with 3n plus 2 if there is no multiplier with n. But don't forget, function at n should be less than or equal to cg at n. So we could introduce a multiplier to our g at n so that it could be bigger. Okay, so let's try 5n. So now, instead of having c is equal to 1, make it 5. So will it become bigger compared with the 3n plus 2? Yes. When n is equal to 1, they are equal. But for the other values, 5n is bigger than 3n plus 2. So therefore, we could say that 3n plus 2, the big O notation of 3n plus 2 is n. It's a family of n. Okay, to make this true, c is equal to 5, multiplier for rg at n, and rn sub 0 or n0 is 1, and beyond 1, Rn or g at n will become bigger compared with the function n. Okay, so aside from the simulation using a table, we could manipulate the equation if you still remember the discrete math approach. Okay, so we could represent, or we could replace 2 by a bigger value. Okay, since we're talking about n, why not introduce n to your 2? Okay, it could be when we introduce n to R2, it could be the same, am I right? Or it could be bigger when n increases, so there's no problem. Okay, so 3n plus 2n, then add 5n. So therefore, 5n is bigger than 3n plus 2 when we introduce n to your 2. So this could be considered as your c g at n. Okay, wherein c is equal to 5, now n is greater than or equal to 1. Okay, so when we manipulate the equation, okay, the original equation of the function, if we want to get a big O notation, we need to make it bigger. Okay, so if you're going to change a certain term, you need to make it equal or bigger when you introduce a value or a variable. Okay, so that will be our second solution for example 2. How about example 3? Now, can we say that the big O notation of n squared is n? Definitely no. As you can see in this table, can we say that n squared will be bigger than n? Definitely no. Is there a multiplier that can be introduced to n so that n squared will be smaller? We could try, but definitely still, in a certain value of n, n squared will become bigger. Therefore, we could not say that OG at n is the big O notation of f n squared.